Let's close the chapter with additional metrics that we'll see later in the CSSE textbook, including your certification exams. We've actually already seen some, and the rest are relatively clear, I would say. And we just saw the first metric, which is the process sigma. And to calculate the sigma, we'll first calculate the process yield. And the calculation to determine the yield, which is the percentage of good outputs, is the number of opportunities. That means how many times the process executes minus the number of defects divided by the number of opportunities. We can then use the DPMO table to determine the process sigma. So let's try an example with a printing process that has 150,000 opportunities each week, meaning that it prints 150,000 items each week. And this past week, 750 were defective. The calculation is 150,000 minus the 750 defects divided by 150,000 times 100, and the answer is 99.5. That means the process produces an estimated 99.5% process yield. 99.5% not defective. We can then use the DPMO table to determine the process sigma. DPMO means defects per million opportunities. And then looking for 99.5% process yield in that right column falls near 4 sigma, which is 99.38. So 99.5 is close, but we can then look at a more detailed DPMO table to specify it. And the actual sigma for 99.5 falls close to 4.1. So our process sigma is about 4.1. It's a 4.1 sigma process with 99.5% process yield, which is fairly good. It's not 6 sigma though, so perhaps we can improve it with lean and/or DMAIC. The next metric is the related idea of DPMO, defects per million opportunities. And DPMO is calculated as the number of defects in the sample divided by the number of opportunities in the sample, then multiplied by 1 million to get the million opportunities part. As an example, a retailer examines the quality of order forms entered by customer service reps, and each form has 10 fields, meaning there are 10 opportunities for error. And a review of 90 forms finds 2 errors. So our calculation is 2 divided by 900, 90 times 10. 90 forms times 10 opportunities for error, 90 times 10, 2 divided by 900 times 1 million is 2,222 DPMO. Then comparing that with the DPMO table, it's between a 4 sigma and a 5 sigma process. And again, the more detailed DPMO table shows us that it's roughly a 4.3 sigma process. Let's look at 3 more metrics, starting with defects per unit, DPU. And that is what it says it is, how many defects are found per unit on average. And the calculation is the number of defects found divided by the number of units in the sample. So if we look at an example with a publisher who prints 1,000 books, so we pull 50 of these for quality checks and found that 3 had missing pages, and then 1 had missing pages plus a torn cover. So that counts as 2 errors. And then 2 had loose spines, and then 1 had incorrect printing and incorrect alignment. So that also counts as 2 errors. So the DPU is calculated as 3 for the missing pages plus 2 for the 2 errors with the missing pages and torn cover, plus 2 for the loose spines, plus 2 for the errors with incorrect printing and incorrect alignment. So 3 plus 2 plus 2 plus 2 is 9, divided by 50 is 0.18. There are 0.18 defects per unit on average. The next metric is first time yield, FTY, which considers defects that are scrapped, meaning discarded. And the calculation is the number of good units produced divided by the number of units entering the process. And another way to say that is the number of units entering minus the scrap divided by the number of units entering the process. For example, if 100 units enter process A and 95 units exit, meaning that 5 were scrapped, then first time yield is 95 divided by 100, which is 0.95. 95% first time yield for process A. We can then extend this to a multiple step process. So for instance, those 95 units from process A then enter process B, which achieves 85 good units, 85 out of 95. And then those 85 units enter process C, where 80 good units exit, so 80 out of 85. That means the first time yield is 95 divided by 100 for process A, 85 divided by 95 for process B, and then 80 divided by 85 for process C. So 0.95 times 0.89 times 0.94 is 0.79. 79% first time yield across processes A, B, and C. Our last metric is rolled throughput yield, RTY, which considers scrap and rework. Rework means defects that are fixed. So first time yield above did not care about rework, so it didn't distinguish rework from regular good items. But rolled throughput yield here subtracts the reworked items, not counting them as good outputs. So the calculation is the number of units entering minus scrap and rework divided by the number of units entering. So notice the difference. It removes the rework. So suppose that process A above achieved its 95% yield because 7 items were reworked. That is 100 units entered and 12 were defective, 5 were scrapped, but 7 were reworked. They're fixed. But we're not going to count these here in RTY. So we remove the scrap and the rework. RTY is 100 minus 12, 5 plus 7. 100 minus 12, which is 88, divided by 100 is 0.88 or 88% rolled throughput yield, RTY. In closing, don't be afraid of math. Engage in it. Use it as a tool to provide evidence to overcome bias and unfounded opinion. Math is your friend.